So now let's do an example for waves on a string. So we have a certain string whose mass is 4.57 times 10 to the negative third kilograms that is 0.620 meters long. That string is capable of producing a wave that has a frequency of 640 hertz and whose wavelength is 1.20 meters. So we're going to have two questions in this part. First of all, what is the speed of the wave on the string? And then secondly, what is the tension in the string? Now, in here, I'm going to go back to our reminders, our basics, that we have two different equations that apply to waves on a string. We have the general equation that the velocity is equal to the frequency times the wavelength. This is an always equation. Love this equation because it works for literally any single wave. We also have the fact that we have a wave on a string, which means we have velocity is equal to the square root of the tension divided by the linear mass density, or the mass divided by the length, all in the denominator. So let's make a list of the things that we have to start. We know the mass, the length, the frequency, and the wavelength. We're trying to find the velocity and the tension. So first of all, that leads me to, hey, I have an easy way to find the speed of the wave, which would simply be that the velocity is equal to the frequency times the wavelength. And we know the frequency, and we're told the wavelength as well. So this is just that straightforward 640 times 1.2, which, according to my handy dandy calculator and a few punchy punchies, we get 768 meters per second. Okay, that's an exact number. Sig figs, we don't have to do any rounding. We can leave it as is. Now, what's the tension in the string? The tension in the string, I'm going to come to my tension equation over here. That velocity is equal to the square root of the tension divided by the linear mass density, which is the mass per length of the string. Now, I'm going to do my algebra before I plug in any numbers because this whole mess right here is ugly. So first things first, I want to get rid of the square root sign. So I'm going to square both sides, giving me the velocity squared is tension over the mass per length. Now I want to get rid of and now I have a fraction within a fraction. So I want to get rid of that fraction within a fraction, which means I'm going to multiply both sides by the denominator, which is that whole fraction there, which leaves me with that the velocity squared times the fraction of the linear mass density, or mass per length, is equal to the tension, T. Well, sweet, I've got all of those numbers. So tension would be my velocity, 768 meters per second, don't forget to square it, multiplied by my mass, which is that 4.57 times 10 to the negative third kilograms, divided by my length, which is 0.620. And again, with the few handy dandy punchy punchies on my Nspire, I'm coming up with, well, actually, it doesn't have to be my Nspire, it could be any calculator, because they're all going to do this. And when I do that, I come out with a tension of 4,347.573677, or to three significant figures, the tension would be 4,350 newtons.